Hey, basically a logarithm is the inverse of an exponential. A logarithm takes an exponential and it gives you the exponent back as the answer. So if this is my exponential and I change that into a logarithm, first of all, the base of the exponent becomes the base of the logarithm. So the base is the same. Your base is a subscript. It's a little number down below. A lot of times when people get writing this stuff quickly, they forget that the base is a subscript. It's a little number down there. Okay. The answer of your exponential becomes the number that gets plugged into the logarithm. So let me put that in parentheses, just kind of show that that's a number inside, kind of like a square root. It's easier to see that something is inside of a square root. It's harder to see that something is inside of a logarithm, but that's what it is. It's on the inside of it. And as an answer, you get the exponent. So that's how we define a logarithm. So we're going to take some time and we're just going to play with this stuff and make sure that you understand really what a logarithm is before we move past that. So you're going to have some problems where all they're going to do is they're going to give you an exponential or they're going to give you a logarithm and they're going to ask you to change it into the other one. So if I take this one and I change it into a logarithm, what would it look like? Yeah. Log base 3 of y equals x. Green's running out. It's not showing up well. Let me change colors. Okay, now it usually makes more sense when we start using numbers instead of just a bunch of letters. So how about 4 squared equals 16? Okay, so there you can start seeing it. So log base 4, 16 equals 2. So I get the exponent back as an answer. It tells me that log base 4, that means that 4 squared equals 16. A lot of times when we go to start solving these, we say 4 to the what power equals 16. That's how we get the answer to a logarithm. Okay, so this next one, if I want to change this into an exponential, what will be the exponential that would be equal? 7 squared equals 49. Okay, so again, your first set of problems are going to be kind of like that. You're just switching them back and forth. And they should make sense. I mean, if you got 49 to the 7th power equals 2, that doesn't make sense at all. Okay, this first one I'm going to do it a little slow just to make sure that we all understand what this is asking for. Okay, so what we're doing here is trying to figure out what it equals. Again, this is asking for the exponent. So what it's asking for is 5 to the what power equals 125. What is it? 3. So every time you go to solve a logarithm, that's what you're asking yourself. So the number 5 would be what? So 2 to the 4th. So if I had log base 6 of 36, what would that be? 2. Okay, do you get the easy ones? Do you need any more examples of the easy ones before we go on to the harder ones? Okay, so how about number 6? Nope. Nope. 1/2. So what you're doing is 9 to what power equals 3? Well, how do you get from 9 to 3? Using powers. Square root. And wherever you're dealing with roots, roots are fraction exponents. So if you're doing anything like a square root or a cube root or anything like that, that's going to turn into a fraction, like 1/2, 1/3. I don't think we'll be sadistic enough to give you anything higher than that. Okay, so how about number 7? -2. Number 7 is -2 because, again, 4 to what power equals 1/16? Well, we know that 4 squared equals 16, but I need that flipped over. So what kind of exponent flips us over? Negative. So to get to 1/16, I make that negative, and then that turns me into a fraction. Okay, I'll give you number 8 and see if you can figure out number 8. Oh, I messed that one up. That's supposed to be a 5. Dang it. I started writing too fast. That's supposed to be a 5 in there. Sorry. You're like, that can't be done. Mm-hmm. Okay, it'd be -1/3. The negative, because we have a fraction that needs to turn into a whole number, so the negative would flip it over. The 1/3, because we're going from a large number to a small number, so the only way we can go from a large number to a small number is by rooting. So a cube root of 125 would turn it into a 5. So that would be -1/3. Okay, the next 4 have a purpose. Okay, no, this one would be 0. Because anything to a 0 power equals 1. Okay, 10 would be 1. I'm hoping you're okay with that one. That would be 4 to the 1 power would equal itself. Okay, 11 I usually think is kind of silly, but it's an actual rule and it has a purpose.
Wait, 11 is
Yeah.
yeah, 11 is
What's it going to be? What's 11? 6. Because this is saying 5 to what power equals 5 to the 6th power.
Oh. Okay. Yeah, I was trying to solve that. That makes sense.
It has a 11 and 12 have a purpose. We just won't get to the purpose until the next unit or the next section. Okay, now 12 takes a little bit more work. It's really easy if you try to glance over it and do it without meaning. You're like, well, the easiest answer would be 5. It is 5. But why? Yeah, the 7 and log 7 cancel out, but why? Well, to do this one, we have to go back to the definition. Turn that into a logarithm. So what I'm going to do is, before I do this, I'm going to make that equal x. And then I'm going to change that into a logarithm. So that would be log base 7 of x equals the exponent, which is log base 7 of 5. Now I was looking for x, right? So what's x? X has to be 5 because I have log base 7 of what equals log base 7 of 5.
Everything is good the same one log as the little the subscript. It's answer is the exponent.
Yeah. So if these two numbers are the same, then whatever's inside the logarithm up here is your answer. And the reason is if we go back and we change it using our definition of logarithms, then we get the same logarithm on both sides. So the answer is just, these two things inside are the same thing.
That makes sense.
Okay, so what that gives us is example 9, 10, 11, and 12 are 4 properties of logarithms. So property number 1 is that log base of anything of 1 is always equal to 0. Again, that's just because anything to the 0 power is equal to 1. Second property follows example 10. If I take log base b of itself, well, then it's going to equal 1. Because anything to 1 is equal to itself. Okay, third rule. Yeah, looks like that. It follows example 11. If you have the base and the exponential base are the same, then the exponent just is your answer. And then the fourth one follows example 12. Sorry, that was a little small there. B log base b of x equals x. Yeah, there's more properties of that. We'll get into the other properties in the next section. But those are the only properties you need for today's stuff. All right, you good with those? Any questions at this point? Because this is really the basis for logarithm. Okay. All right, we have two special types of logarithms. These are the ones that show up on your calculator. It's kind of like square root. We have tons of different roots, but we really only have two roots we ever really use, square root and cube root. So those are the only two that actually show up on your calculator. And square root is special in that we don't put the little number up there. Well, we have two special logarithms that we use so much that we don't put the little number up there. One of them is log base 10. This one is used the most. So much so that we got lazy and we dropped the little 10 off. So anytime you just see a log, that's log base 10. Log base 10 is used on everything. Your tornado scale, your earthquake scale, your sound decibel scale. Anything that's a logarithmic scale is log base 10. The other one is log base E. And it's ln. Stands for log of the natural number. That's why they use ln. So those are the two that show up in your calculator. So I just wanted to make sure that you guys are okay with using your calculators. So I was going to do these two, and just you can try them on your calculator. Again, somewhere in your calculator you should have a log and an ln button. And you should literally have a button that says log. You should have a button that says ln. Sometimes the ln button might be above the ex button, or the ex button may be above the ln button, depending. Usually you have one and then the other one is a second of the previous one. Like on my calculator, the ex button is the second of the ln button. Okay, so let's see. Turn on, you stupid thing. Log 32 is 1.505149978. Usually I'll have you guys round off to 2 decimal places. So that'd be 1.51. And then ln of 11 is 2.397, so it'd be 2.40. So again, the only reason I'm doing that is just so you guys can double check, make sure you're using calculators correctly. Some calculators you put it in exactly how it is. Some calculators you put in the number, then you hit the log button. Like I know on my iPhone, I have to put in the number and then hit the log button. Now, I know with fancier calculators, there's a way that you can put in the entire thing. With the normal calculators, you can't put in anything besides log and ln. There's a change of base formula where you can put in other things. We will get to the change of base formula in the next section. They didn't put it in this section because you really don't need it. Because all the problems they give you are either the ones where they want you to solve them without calculator, or they're calculator-based problems like these, where they actually give them to you like this. All right, general functions. Or general function. This is basically for graphing. When we graph, again, it looks like normal. All letters mean the exact same thing they normally mean. That's why when we started off and I told you A, H, and K would keep coming back and coming back and coming back and coming back. Yeah, they never go away. When we get to second semester and we're graphing trig functions, we still use A, H, and K. All right, so basically we have graphing to do. And then we're done. I think we can get it done. I don't know. Depends on how you guys do with this. If you're struggling and ask questions. I don't want to rush through this. If it's not making sense, it's not making sense. If we don't get very far through it, that's fine. Graphing is where usually people struggle the most.
Yeah, I think it's really struggle.
That's fine. If we need to finish up graphing tomorrow, that's fine. If I don't have enough examples and we need to do more examples, that's fine. Again, it's whatever you guys need. I want to make sure you have what you need. And whenever I teach Algebra 2, we spend so much time on graphing that we split this chapter in half. We spend a lot of time on graphing exponentials and logarithms, then we have a test over graphing exponentials and logarithms. Then we go over the algebra stuff, and then have a test over the algebra stuff. Unfortunately, in here, we don't do that. Okay. The base graph. First of all, logarithms are the inverse of exponentials. So exponentials have an asymptote that is horizontal. So the inverse of a horizontal line is a vertical line. So logarithms have an asymptote that is vertical. So since the base asymptote for an exponential is along the x-axis, the base asymptote for a logarithm is along the y-axis. So this is where the asymptote for the base asymptote for a logarithm is. Now, we can go ahead and talk about it here. We don't need it, but since it's vertical, which one would move it, H or K? H. Think about, K moves things up and down, right? So if I take this vertical line and I move it up, there, I moved it up. Did it move anywhere? No. So K is going to shift it up and down, but that doesn't move it anywhere. So in order to actually make it move, H is what's going to move it. So now your asymptote is going to be affected by H. Yeah. Except for 18. When we get down to 18, that one's going to be affected. But yes, all the others, 15, 16, 17, they'll all be at 0. So H is what's going to affect it. So down here, when we get to this one, that's the number that affects it. Okay, when we do a logarithm, the first thing that we know, whenever I plug in 1 into a logarithm, what do I get? 0. So it's kind of like our starting point on an exponential. When we plug 0 into an exponential, we always got 1, right? Well, this is inverses. Remember, with inverses, our order pairs switch around. So this ordered pair in an exponential becomes this ordered pair in a logarithm. Right? We can't have anything at 0 because 0 is an asymptote. But what we do have is we have, I should change color. That's my asymptote color. What I do have is I have that dot. That's kind of my starting point on all my graphs. Is 1, 0. Because it doesn't matter what the logarithm is, if I plug 1 into a logarithm, I always get 0. Now, what number can I plug into this logarithm and get a whole number answer? What's the next number I can plug in and get a whole number answer? 3. Right? If I plug 3 into this, I'll get a whole number answer, correct? I'll get 1. So 1, 2, 3, 1. What would be the next number I could plug in and get a whole number answer? 9. So the x values you plug in would be the powers of 3. So I could plug in 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I could get 2 back as an answer. Now, the next number that I could plug in is going to be 27. Don't want to plug that one in. Okay, but going backwards, I don't have anything below here. Well, my graph actually does go below here. So what number could I plug in between here? 1/3. If I plug in 1/3, what do I get for an answer? -1. Right? 1/3, if I plug in 1/3, one-third is just 3 flipped over. So that would give me -1 for an answer. Now, I can't tell, I mean, that's just guessing. And my next point that would actually give me a whole number answer would be 1/9, which would really get insane.